most frequently used one. If you select the nonlinear, you always basically, if you don't specify, this is the default setting of SVM. This is the default choice. Now, your problem is pretty simple. Again, you want to minimize this margin. Oh, yeah, the margin is reversed. It's 2 over this, right? You want to maximize the margin. That's the minimize the reciprocal of the margin. Can you see that this is the reciprocal of the margin? The margin is 2 out of this W squared, right? Right? The distance. And that you want to minimize this is equivalent to maximize the margin. This 2 over W squared. And the subjective, you only change a tiny bit here. This is the weight. That's the weight function to give her, and this is the transformation to the original point. So that's it. Mathematician, our job is really write out your problem into the quantitative measurement. That's our job. And once you build this, now it's a standard mathematics problem. Again, we're going to use the quadratic method to find the solution. Lagrange multiply. This is a mature field in theory and in practice. So there's a sort of algorithm to do it. So the procedure to use this, doesn't matter what tool you're going to use. First, you need to change the data into the SVM package, whatever tool that have a specification. For example, if you use R, you need the first column to be the class. And if you use the wake-up, the last column is the class. That's a little tiny difference you need to know. Otherwise, garbage in, garbage out. So, second, conduct the simple scaling of the data. What do you call it? Scaling? More is better to call it normalizing. Normalizing the data. Don't make some data get all the noise, the voice, and the other one all just shadow. It's just cannot see because they're too small. And then you consider the kernel. This is a standard kernel, but there are different kernels. This kernel is your transformation function. And then in the model, you have this parameter C. Anybody remember what's that parameter C for yesterday's model? And the sigma. Sigma is the standard deviation. Those things you have to try and adjust it, try again to find it. Now, this C is a different model. We did not see the C in this model. Actually, because you don't have a clear cut. Regardless of what way you use, you always have some error of your classification. That C is the penalty coefficient to the classification error. And here we give you a simple model. The true model you have add C times sigma, and we just add it. The true model, you need to add C sigma, the error function, to then 2 power or 1 power depends. Those are the error classified. And this one, you need to always try to see how much penalty give you the best based on the validation data, not the training data. The training data always can make this perfect, but that's not necessarily work good for your testing data. Then, once you find this C and the sigma, this is the sigma. This is sigma. That's what I write wrong. You can use gamma to train the whole set and the test, train again, test it. This is called research because you know, oh, the theory works fine. But once you practice it in, you might get a very lousy result. until you keep doing it. Each time you improve a little bit to be good enough. When you do project, you're going to see that. So this is a powerful method, but not as easy as the other decision tree or based method or the nearest neighborhood. It's not easy to use, but it could potentially give you the best result because it's a dual optimization, give you the best choice, a trade-off between the margin and the error, and you have a lot of flexibility. Then you have a lot of complexity too. That's a trade-off, right? So that's why this is the most frequently researched method. By the algorithm itself, I can show you how tedious it is. In the book, if you really want to do it, maybe it's good to take it home for the graduate students. And you're going to change into the dual problem. The dual problem have no weight here. It's just this lambda. This is the Lagrange multiply. Put this multiply in here, and you find that this is the weight, which is those are the 4 points. And the weight can write into the Lagrange multiply. You want to solve this equation. That's the dual problem. And that you have 5 variables, 5 equations, standard linear equation. You can solve it. And once that's the algebraic package. Once you solve this, you got all this multiply, and this is the intersect point. Is this one cutting the line, the B. When you get this, you get the weight. Once you get the weight, you just plug in back into this weight function here. And when the dot, and you all do all those calculations, it's nothing more than a quadratic function. Which quadratic function? I did all my hand calculation. Is this? Is that a function? x1, x2, or g1, g2 if you want. And then that separate line is the parabola here. Can you see it? And you see the first point here, and here is in one class. These two are in another class. Can you see it? One is in the between of the parabola, one is out of the parabola. Can you see it? If you look at the cut.
Maximize the...
Yeah, then you maximize the margin. It's really all the way from this point to this point. You can get the maximum margin here and here. Can you see it? It's in the middle. That's no surprise. What's a hyperbola? Hyperbola means the equal distance. The difference of the distance is equal. That's how you do the hyperbolic position. Give me an example. If I have the AUV, it's working outside, and I use acoustic, try to measure the distance, where is the position. I have this triangulation, but the very noisy environment, not reliable. The easy, because your clock, you need to rely on time. Your clock is also error. A good way to do it is use hyperbolic positioning. You just get the 3 observations. You let this AUV shoot for the sonar and have 3 positions to receive it. Because the time difference is always the same. And use that difference, you can use 2 of the parabola, then you can position it. Each parabola just means when you receive the signal, tell you what's the distance, right? And if 2 receive the signal in a different position, I get that parabola. That's what it is. And the other one also got another set of parabola because of the distance difference. And then you got the position. That's the best way. And that could be another research project. So that's not by surprise. This was separate way off from here, here the difference there, here is the same, and the separate in the middle, and here, see, the distance is all 1/2, right? That's the maximum you can get. So that's the nonlinear idea. The calculation, by the way, nobody do it by hands. Even 4 points by hands is so complicated. Don't mention you got thousands of points. But you have different algorithms. Most algorithm is so-called gradient, because once you already know which function you want to minimize, you always can take the direction of the gradient, means you're going to maximize the decreasing. You can decrease it fastest. And they always decrease until you cannot decrease anymore. Then you say that's your solution. It's as simple as this. This is almost used everywhere. Everywhere. We call it gradient algorithm, or say gradient algorithm. Just a G-R-E-E-D, grid. You always just, you know your goal. And each computation round, you just need to make sure you get a better result. How do you get a better? You don't random go to get a better. You get a gradient algorithm and just see where I can get it down very quickly in the slope. I will make Newton's method. Start off from Newton's method in the 1D, and later on you go to Gauss, to everybody. Use that idea. So they can do it.